Welcome to the deep dive. Our goal here, really, is simple. We want to give you that shortcut to being genuinely well-informed.
Without getting bogged down.
Exactly. And today we're embarking on a truly mind-bending journey.
Absolutely. We're
Yeah.
diving straight into the cosmic insights of Stephen Hawking.
Pulled directly from his incredible work, A Brief History of Time. We've gone through it carefully,
Yeah, we have.
and we're aiming to, cut through the complexity.
And just pull out the most fascinating, maybe surprising bits about the universe.
And our place in it, right?
Right. And this isn't just about listing facts. We're tackling fundamental questions.
The big ones.
The nature of reality, time, space, gravity, even quantum mechanics.
That weird stuff.
It is. And we'll connect these ideas, all from Hawking's work, to give you a grounded perspective on concepts that maybe feel a bit fuzzy usually.
Okay, let's start with maybe the biggest shift. Time and space. How we used to think about them.
And it's pretty straightforward, wasn't it? Like a railway line.
Yeah, exactly. Hawking uses that analogy. Time was just this track, going one way. Fixed.
A constant backdrop for everything. But then, Einstein.
Ah, yes. Everything changes. His big idea.
That time and space, they aren't fixed at all. They're relative, dynamic.
Okay, let's unpack that a bit. Relative dynamic.
It means time isn't this universal clock ticking the same for everyone. It's actually personal.
Personal. So my time could be different from yours.
If we're moving at different speeds, yes, you'd literally measure time differently.
Wow. But something is constant.
The speed of light, that's the key. It stays the same for everyone, no matter how fast you're moving.
And this wasn't just a theory, right? There was proof.
Oh, yeah. Crucial experiments, like the Michelson-Morley one. It showed light speed doesn't change with the observer's motion.
Which just completely threw out those old ideas of absolute time and space.
Totally upended them. It's fundamental to understanding everything that follows.
So space and time are flexible, dynamic. That's already huge. How does this kind of thinking apply to the very beginning, the universe's origin?
Right. This takes us straight to the Big Bang Theory.
The origin story.
Exactly. Hawking presents it as everything started from this incredibly dense, incredibly hot state.
Way back when, about...
Roughly 13.8 billion years ago.
Yeah.
And from that initial point, it's been expanding rapidly.
And cooling down.
Gradually cooling, yes. Which allowed, atoms and structures to actually form.
And then galaxies.
Gravity pulled matter together, forming galaxies. And that expansion, it's still going on.
And Hawking points out something specific, doesn't he? About how matter even formed.
He does. It's about something called the exclusion principle.
Yeah.
He says, if the universe had been created without the exclusion principle, quarks would not form separate, well-defined protons and neutrons.
Okay, the exclusion principle. What's that, basically?
It's like a fundamental rule saying
Yeah.
certain particles, quarks in this case, can't be in the exact same state. They need their own space.
So without that rule...
Protons and neutrons, the building blocks of atoms, just wouldn't form properly. No structure.
Wow. So the rules had to be just right.
Precisely. And we can actually see the evidence for this expansion.
How?
Edwin Hubble. His observations showed distant galaxies are moving away from us. That's the proof. It supports the whole model.
Okay, from the massive scale of the universe, let's zoom way, way down.
To the subatomic.
Yeah. Quantum mechanics, you mentioned it earlier, it's different.
Radically different from classical physics, yes. The core idea, it's all about probability.
Probability, not certainty.
Exactly. Unlike the old view where things had definite positions and speeds, quantum mechanics says particles exist in probabilistic states.
Meaning
There isn't one single outcome for an observation. There are multiple possibilities. Hawking puts it perfectly.
what does he say?
He says, quantum mechanics does not predict a single definite result for an observation. Instead, it predicts a number of different possible outcomes and tells us how likely each of these is.
So a particle isn't just here, it could be several places at once. Until you look.
Sort of, yeah. It exists in a superposition of states, and the act of observing it actually forces it into one state.
That's bizarre.
It is. And you also can't perfectly measure both its position and its speed simultaneously. There's a fundamental limit.
The uncertainty principle.
That's the one. And maybe the most profound thing is that randomness seems built in. It's not just us not knowing enough.
So the universe is fundamentally uncertain at its core.
That's what quantum mechanics suggests.
Yeah.
It really challenges any idea of a perfectly predictable, deterministic universe.
Okay, let's zoom back out again. To the big stuff.
Right. Galaxies, stars.
And what holds them together? Gravity. But isn't there a paradox here? It's supposed to be the weakest force.
It is, by far. Yet it shapes everything on a large scale.
How does that work? How can the weakest force be so dominant?
It's a great question. Hawking explains it really clearly. He points out two special properties gravity has. He says, gravity is the weakest of the four forces by a long way. It is so weak that we would not notice it at all were it not for two special properties that it has. It can act over large distances, and it is always attractive.
Ah, so it's weak individually, but it reaches everywhere and always pulls things together.
Precisely. It doesn't repel, it just attracts. And over cosmic distances, that adds up. It dictates how stars form, how galaxies cluster.
And it's key to understanding black holes, I imagine.
Absolutely, and cosmic evolution in general. But Einstein's contribution here was massive too.
General relativity.
Yeah. He transformed how we see gravity. It's not just a force pulling things.
What is it then?
It's geometry. The curvature of space-time itself, caused by mass and energy.
Like a bowling ball on a trampoline.
That's the classic analogy, yeah.
Yeah.
Massive objects warp space-time around them, and other objects follow those curves. That's gravity.
Okay, speaking of extreme gravity, black holes, the ultimate cosmic monsters, right? Eating everything.
That was the image, definitely. Just inescapable voids.
But Hawking's work threw a spanner in the works, didn't it?
A huge one. He showed something completely unexpected. Black holes. They aren't actually black.
Wait, what? Not black?
Nope. Because of quantum effects near their edge, their event horizon, they actually emit radiation.
Radiation?
Yeah.
Seriously?
Yeah. It's called Hawking radiation now. It means they have a temperature, albeit incredibly low for large ones.
And if they're radiating energy?
They lose mass, which means over truly immense timescales, they can actually evaporate, disappear.
So they aren't eternal prisons after all. They can just fade away.
Incredible, isn't it? It completely changed our understanding. They're these amazing natural laboratories where gravity and quantum mechanics meet.
And Hawking noted they were theoretical long before we saw evidence.
He did. He said black holes are one of only a fairly small number of cases in which a theory was developed in great detail as a mathematical model before there was any evidence from observations.
A testament to the power of pure thought, almost.
Absolutely.
Yeah.
And now observing things around black holes helps us test these fundamental theories.
It really blows the old image away, which makes you think, what's the ultimate goal here for physics?
Well, the grand ambition, the sort of holy grail, is a theory of everything.
A single theory to explain. Well, everything. All the forces.
Exactly. One framework that unites gravity with the other fundamental forces, the electromagnetic, the strong and weak nuclear forces.
Are we close? What are the big ideas being explored?
There are several approaches. String theory is perhaps the most famous one. Then there's quantum gravity, grand unified theories. Some even explore extra dimensions of space.
But there must be huge challenges, right?
Oh, absolutely. The biggest hurdle, really, is getting quantum mechanics and gravity, specifically Einstein's general relativity, to work together.
They don't play nicely.
Not yet. Their mathematics, their descriptions of reality, clash at very small scales or very high energies, like inside a black hole or at the Big Bang.
So reconciling the physics of the very big with the physics of the very small.
That's the core problem. But the hope, as Hawking put it, is to find that complete, consistent, unified theory that would include all these partial theories as approximations.
It's an incredible goal. Let's shift focus slightly back to something we experience constantly, time. But specifically, its direction. Why does it only seem to flow one way, past to future? Why don't we remember tomorrow?
Ah, the arrow of time. This ties into something called entropy.
Entropy, that's disorder, right? Things breaking down.
Essentially, yes.
Yeah.
The second law of thermodynamics says that in a closed system, disorder or entropy tends to increase over time.
Okay. How does that give time a direction?
Because the universe as a whole tends towards increasing disorder. This creates a fundamental asymmetry between past and future. The past had less disorder, the future will have more.
So we experience time flowing in the direction of increasing messiness.
That's a good way to put it. Hawking stated, disorder increases with time because we measure time in the direction in which disorder increases.
Are there other eras of time?
He discusses three main ones. The thermodynamic arrow we just talked about, increasing entropy. Then there's the psychological arrow.
Our sense of time passing, our memories.
Exactly. We remember the past, not the future.
Yeah.
And finally, the cosmological arrow.
Which is?
The fact that the universe is expanding rather than contracting These arrows generally point in the same direction.
So our perception of time isn't just subjective, it's linked to these fundamental physical processes.
Deeply linked to the universe's expansion and its tendency towards greater randomness.
Okay, thinking about beginnings and the universe's nature, Hawking proposed something really radical, didn't he? Something about the universe not needing a start.
Yes, the no-boundary proposal.
Yeah.
It's quite mind-bending.
Go on.
Think about the surface of the Earth. It's finite, right? You can measure its area.
Yeah.
But it has no edge, no boundary. You can travel forever and never fall off.
Okay.
Hawking and Jim Hartle proposed that space-time, especially in the very early universe, might be like that. Finite in extent, but without a boundary or an edge.
So no starting point, no singularity where the laws break down.
Potentially, yes. If space-time is finite but boundless, there's no initial moment, no point of creation in the traditional sense. The universe wouldn't need an external cause to kick it off.
It just is.
It could emerge from quantum fluctuations, governed by its own mathematical consistency, as Hawking put it quite starkly. The universe would be completely self-contained and not affected by anything outside itself. It would neither be created nor destroyed. It would just be E.
Wow. That completely challenges how we usually think about origins.
It absolutely does, both philosophically and theologically.
It makes you reflect on the nature of science itself. If we can propose ideas like that, what is a scientific theory according to Hawking? Is it absolute truth?
Not at all, actually. He had a very pragmatic, almost humble view.
Which was?
He said, a scientific theory is just a mathematical model we make to describe our observations. It exists only in our minds.
Only in our minds. So it's not reality itself.
It's our description of reality.
Mm.
A tool. Theories have to make predictions we can test.
Right. They have to be testable, falsifiable.
Exactly. And they're always provisional. They can be revised or replaced if new evidence comes along. They're approximations, getting better over time, hopefully, but not the final word.
So science is this ongoing process of refining our models, not finding ultimate truth.
That's the picture he paints. It emphasizes intellectual humility, recognizing the limits of our knowledge.
Okay, let's bring this incredible journey through the cosmos back home to us, humanity.
Our place in all this vastness.
Yeah. Given all these laws, the expansion, the quantum weirdness, why are we even here to talk about it? It seems improbable.
It does, doesn't it? This leads to something called the anthropic principle.
Anthropic.
Yeah.
Meaning related to humans.
Yes. In its simpler forms, it basically says that the universe's properties must be such that they allow life like us to develop, because otherwise we wouldn't be here observing it.
Kind of a self-selection thing.
A bit, yeah. But Hawking highlights the deeper implication. The remarkable fact is that the values of these numbers, the fundamental constants of physics, seem to have been very finely adjusted to make possible the development of life.
Finely adjusted, like a dial turned just right.
Exactly. If things like the strength of gravity, the charge of an electron, were even slightly different,
What would happen?
stars might not form, or atoms might not be stable, chemistry wouldn't work, life as we know it would be impossible.
So our existence seems to depend on this incredible cosmic coincidence.
It certainly looks that way. The emergence of complex structures and ultimately consciousness from the simple conditions after the Big Bang seems extraordinarily unlikely.
It makes you wonder, is it just random luck or is there something deeper going on?
That's the profound question it leaves us with, isn't it? It forces you to reflect on randomness versus, well, something that looks like design, even if it arises naturally.
We've covered so much ground, from time being personal to black holes radiating away to the universe perhaps just being without a start, all from Hawking's work.
It's incredible stuff.
Hopefully distilling these ideas has given you, our listener, some really impactful things to think about, a real shortcut to the core concepts.
Definitely. And as you reflect on all this, the nature of time, the weirdness of the quantum world, the fine-tuning that allows us to exist, maybe ask yourself, what stands out most to you?
Yeah, what resonates?
How does grappling with these huge scientific ideas shift your own perspective? On reality, maybe? Or just your place within it all?
Good questions to ponder.
Remember, this deep dive gives you a solid footing, but the real adventure is keeping that curiosity alive. Keep asking those big questions.